So in today's class, we are going to talk about gear design. In last class, we talked about friction wheels. So think about, like, you have one wheel, then you have another wheel. They are making a contact, and this is called as point P, which is point of contact. And clearly, we talked about it. This is line of centers. So this is the line that is joining the centers. And as we discussed in last class, law of gearing states that the point of contact should lie on line of centers. If it does not lie for some reason, the power transmission will not be continuous and it won't be smooth. So this actually introduces us to a concept called as pressure angle. Now, if you think about the friction wheels, what is causing this big gear to rotate this small gear? So since these two gears are in contact, and if I were to rotate the big gear, I'm going to call this big gear, and I'm going to call this small gear. What makes this big gear rotate the small gear? So consider, let me do a thought exercise. So these two gears are in contact. I'm rotating the big gear, small gear is in contact. The small gear or small wheel, I should not call gear, I should call wheel. So this wheel rotates. Now what I do is I add oil. So there are oil droplets. In other words, the surface becomes super smooth. Now you would notice that these two wheels, even though they are in contact, even though the law of gearing is satisfied, they will start slipping. And the reason for that is there is not enough frictional force between these two wheels to transmit the torque from big wheel to small wheel. So what it means is, if you have friction wheels, if the friction is absent, we will not have any power transmission. Now, we talked about this in last class. So if I were to show you the force or the normal reaction, the arrows show the normal reaction. And the frictional force is something like this, which is mu times F. So this frictional force is mu times F. That is the cause of power transmission, because when this frictional force gets multiplied by the radius, the torque is transmitted. And this radius could be the radius of the small wheel, or this could be the radius of the large wheel. That means, let me rewrite this equation. Torque on the big wheel is going to be mu f times the radius of the big wheel. Torque on the small wheel will be the frictional force multiplied by the radius of the small wheel. Clearly, the torque on the big wheel is going to be greater. Torque on the small wheel is going to be less. Now, let's understand one thing real quick. So if you think about the power, I'm going to express power in three relations. And I want you to understand this very carefully because this is the crux of gear transmission. Power is equal to force times velocity. So if I have a frictional force mu f, multiplied by the velocity of p is nothing but the power that is at the point of contact. This power is at the point of contact. So this is very important. So this is power at point of contact. P. Now please note this point of contact can be thought, this is shared by the big wheel and the small wheel. In other words, this power P is equal to the power of the big wheel. I'm going to call this BW. Power by the big wheel. Please note, big wheel is not translating, it is rotating. So this is torque of the big wheel multiplied by angular speed of the big wheel. So torque of the big wheel is mu f multiplied by RB multiplied by omega, I'm just going to call omega b. If you were to think about this point of contact as the point on the small wheel, so I would say SW, this is going to be torque of the small wheel multiplied by omega of the small wheel. Torque of the small wheel is mu f times RS, and I'm going to call this omega s. Now, if you were to look at this equation and this equation, since the left-hand side is the same, the right-hand side is also the same. So I can say PP is equal to mu f times RB times omega b is equal to mu f multiplied by RS multiplied by omega s. That means if I were to cancel UF on both sides, I get the relationship that we derived in last class. Or alternate form of the relationship, which is TB times omega b is equal to TS times omega s. And with those two equations, you can actually rewrite the equations from, I'm going to say this is equation 3, this is equation 4, and these sets of equations give you the equations for power transmission. What it means, as the speed of the gear increases, the torque on the gear decreases. As speed of the gear decreases, torque on the gear increases. So this is the equation that we derived in last class, but this equation comes from the law of gearing. Now, what are the limitations of friction wheel? So in friction wheel, you have this unwanted dependence on mu. So for example, if mu becomes zero, then there is no power transmission. So there is no power transmission. So how do we account for this? The other thing which I want you to think about is this is the force vector F. This is the force transmitted. And this transmitted force is making 90 degrees. And this is very important. This transmitting force makes 90 degrees with line of centers. And this transmitted force makes 0 degrees to the line that is perpendicular to the line of centers. So this is an important observation. So F is perpendicular to line of center, and F is at 0 degrees to line perpendicular to line of centers. And I want you to think about this equation or this expression for a second. So YF is at 0 degrees to the line perpendicular to line of centers. And the reason for that is the equation frictional force F is equal to mu n. Frictional force is perpendicular. Frictional force is perpendicular to normal reaction. Now what I'm going to do is, I would like to take the dependence on the friction out. So I'm going to create a profile. So instead of having a circular wheel, I would actually try to cut some teeth. But I cannot cut teeth randomly, because then they will not engage and disengage smoothly. So let me talk about smooth engagement. So what I'm going to do is, we have these two wheels. And I'm going to cut some teeth on these wheels. So what I'm going to do is, I'm going to have a tooth on the big wheel, another tooth on the big wheel, another tooth on the big wheel. And I will have teeth on the small wheel. And one thing I just want to let you know, sometimes this is called as the blank, where when we cut the gears is blank. So now I have teeth on the big wheel and the small wheel. So if I were to take a zoomed view, it will show something like this. There is one tooth and there is another tooth. So these two teeth come in contact, and at one time there will be a line contact, just like friction wheels. And this point is called as point P. This point P is the line of center for these two wheels or these two gears. Now this profile is super important. This is called as the tooth profile. Now I want you to understand what happens. As these two teeth engage with each other, initially the contact starts here. Then gradually the contact progresses around the profile, and then the contact is broken, it exits, and the second tooth comes in contact. And we want this contact to be smooth. The one way the smooth contact can be achieved is creating a profile that rolls onto a circle. So think about it. So if I have a circle, if I have this line, this is a circle. What I'm going to do is I'm going to roll this line on this circle. And I will try to trace one point that this line actually tracks as it rolls around the circle. And this profile is called as involute profile. And teeth, they typically have involute profile. Now, as an experiment, if you were to construct or if you were to 3D print rectangular teeth, so say what I do is, just for the sake of discussion, I create a gear with rectangular teeth. And then if I were to engage this rectangular teeth gear with another rectangular teeth gear, they will not rotate. So rectangular teeth will lock. They will not roll smoothly on the surface, because for rolling, this involute is needed. There is a particular profile that can achieve the smooth rolling on the profile, and for that you need this profile. The second way to do it is, rather than rolling a line, I roll a circle. So rather than rolling a line, I roll a circle. And if I were to trace the point of contact, then that point of contact again creates a profile, and that is called as cycloidal. Cycloidal. Profile. So gears can have two types of profiles. Usually gears can be cut using two different profile tools. They could have involute profiles, or they could have cycloidal profile. And depending upon application, there are advantages and disadvantages. So for an example, involute teeth are easier to cut. The pressure angle you can maintain constant. In the cycloidal gear, they are stronger, but they are usually specialty gears, so they are expensive. In the case of involute gear, since we are cutting the gear with an assumption that you have a circle and a line, it's not 100% interference free. Because if you think about it, we have two circles. We have two circles that are rolling on each other. So which means involute profile will have some interference. Cycloidal profile will not have any interference. But typically, cycloidal profiles are used in specialty applications. Involute gears are used in common applications. There is one special case where one gear is a straight line. So think about, you have a gear with infinite radius. So in that case, you have something like gear, and then you have a rack. And this rack is actually a flat gear that actually takes the rotary motion of the pinion. This is pinion. And converts into reciprocating motion of rack. So this is very commonly used in steering mechanism. So your car's steering, or usually they have power steering, they have rack and pinion type of gear attachment. The next thing I want to talk about, and this is an important point, since this point of contact is, even though it is at line of center, the force transmission is not perpendicular to the line of centers. So in the friction wheels, we saw that force is transmitted along the line which is perpendicular. But in the case of gears, the force makes an angle. So this force is transmitted at an angle. And this angle is called as pressure angle. In the case of friction wheels, pressure angle is 0 degrees. In the case of gears, your pressure angle can be usually 14.5 or 21 degrees. And this is, so we want to achieve a couple of things with the pressure angle. So if you think about the pressure angle, this pressure angle takes place or comes into picture because the profile is not a straight line, it's an involute profile. You would observe that when you have friction wheels coming in contact, the point does not translate on the profile. In this case of gear transmission, the contact actually gets translated over the profile. But no matter what, that point of contact must lie on the line of center. There are different types of gear teeth depending upon the manufacturer. There is something called as the full gear, and there is something called as the stub gear. So full gear is the full profile is cut. In the case of stub gear, the top of the gear profile is shaved off. So think about it like this. If you have a full gear, it would look something like this. In the case of stub gear, what you would do is you will take a grinding wheel, circular grinding wheel, and shave off the top part. So basically the exact same, but the top part is maybe a little bit of top part is shaved off. So this is called as the stub gear. And again, there are advantages and disadvantages of these gear profiles. Many a times we use full depth involute systems. Sometimes we have to go with the stub gear because we want the gear to be stronger. And why do we get stronger gear? Because let's look at the way this gear can fail. The simplest way to imagine gear is think about it as a cantilever beam. So I want you to think about the gear as a cantilever beam. Clearly, it is not the beam with uniform cross section, but nevertheless, it's a cantilever beam. In the case of full gear profile, the lever arm is high. In the case of stub gear, as you can see, we do not have the top part. The lever arm is short. When the lever arm is short, what it means is the amount of torque or amount of moment that is on the base of the gear is less. In other words, the gear is stronger. So that's why the stub teeth or stub gears are stronger. Sometimes what they do is you have certain restrictions on the center distance. So for center distance, it is important to note the center distance between two gears is nothing but the radius of the big gear and the radius of the small gear. So center distance CD is RB plus RS. And sometimes you shave the gears to maintain the constraints on the center distance. So you want center distance to be particular, say 202 millimeters. So what you do is you shave off the gears or grind the gears and make it into stub gears so that these two gears fit into the center distance requirement. Now, next thing is what are the parts of the gear? So this is called as the gear nomenclature. And this gear nomenclature is same or mostly similar for the Spur gear and the Helical gear. So let me draw a simple gear. So as you can see, this gear can be thought of, it is inside two circles. So you can think about the gears as something between two circles. So the top part of the gear is called as the face, or the top, and top part is called top land, and the side part is called as the face. So let me draw a three-dimensional view. So this is called as the top land. Side part, this is called as the face. This is called as the flank. Now, there are some important dimensions that we should talk about. If I were to replace the gear with an equivalent friction wheel, if I were to replace the gear with an equivalent friction wheel, the diameter of that friction wheel is called as the pitch circle diameter, or called PCD. So this is the center line. So this is called as the pitch PCD. And this is a super important dimension for the gear. So I'm going to write this down. PCD is pitch circle diameter. And what this means, if gear is replaced by a friction wheel, dia of friction wheel is PCD. Now, what happens here is the top of the gear. If I were to draw a circle to the top of the gear, this is called as the addendum circle. So if I were to draw the circle to the top, that is called as addendum circle. If I were to look at the bottom of the gear, and if I were to actually draw uh, a, a circle to the root of the gear, this is called as the root. So this is the root. So if I were to draw a circle to the root of the gear, this is called as the dedendum circle. Now, the vertical distance between the pitch circle diameter and the addendum circle is called as addendum. So this is called as addendum. This is the distance between the pitch circle diameter and the addendum circle. The distance between the pitch circle diameter and the addendum circle is called as addendum. Then the total distance, if you were to add addendum and addendum, that is called as the total depth. So this is total depth. And if you were to look at the face width or the width of the gear on the top, it's called as the face width. And these all different profile nomenclatures have certain proportions. But at this point, I just want to tell you about one important parameter that I want you to remember. So if you were to look at the point on the pitch circle, two successive points on the pitch circle corresponding to the beginning of the teeth is called as the circular pitch. So this distance is nothing but CP. And this is quite important. So I will show it again here. So consider these two teeth. This is the beginning point. This is the second point. And the distance between these two is called circular pitch. Now, circular pitch, CP, is given by a very important relationship, which is called pi times module. And I will talk about this expression in just a second. So the most important equation in the gear design is this: pitch circle diameter is equal to module times number of teeth, where M is module and T is number of teeth. So what I'm going to do is I'm going to multiply pitch circle diameter by pi. So I'm going to call this D is equal to M times T. So I'm going to have pi D is equal to pi times M times T. And then what I would do is I would rewrite this equation something like pi D divided by T. Pi D is nothing but the circumferential or the perimeter of the pitch circle, perimeter of the pitch circle divided by number of teeth gives me circular pitch. So this equation is Cp and pi d over t. If I were to take this t on the other side, gives me pi times m. So what this means is circular pitch is pi times m. But the key equation here is d is equal to m times number of teeth. This is the key equation in gear design. Module is the design parameter for the gear. So let me state this again. This is so important. Gear design is in essence determination of module. For two gears to be in contact, they must have same module. So same module for gear pair. So if you have two gears that are used for power transmission, they must have same module. You cannot mesh a 4mm module gear with a 5mm module gear. Those two gears will not mesh, and that's why module happens to be the fundamental parameter in the gear design. Now, what I want to do is I want to give you some proportions that will be super helpful as we design the gear. So gear dimensions are expressed in terms of module. So gear dimensions are proportional to module. So for an example, addendum is typically 1 times module for full depth system. Dedendum is equal to 1.25 times module. Working depth is equal to 2 times module. Then minimum depth so this is the lowest point on the tooth is 2.25 times module. Tooth thickness is equal to 1.5 times module. Clearance is equal to 0.25 millimeter. And slit radius (0.4 times module. This is not millimeter, this is module. And there could be slight variations depending upon whether you have 14.5 system, whether you have 20 degrees system. But in short, if you know the module, uh, you would have to use. I mean, if you are designing a gear, the module is used as the principal dimension that is used to design the gear. And I don't expect you to remember all this. All these dimensions are given as in table 28.1 in the textbook. The other important thing is, this is pertaining to the involute gears. Involute gears are made using an involute profile. And the involute profile is rolling a line on a circle, which means for certain number of teeth, the interference may be possible. So for involute gears, if the number of teeth are less than equal to 14, actually less than 14, then interference may be possible. So interference is not possible for cycloidal gears, but for involute gears, if you decide to construct, or if you have an involute gear of maybe 10 teeth, then it may so happen that that gear may interfere with the machine gear or lock with the machine gear. So there is a mathematical derivation that I'm going to skip, which talks about the minimum number of teeth on the pinion to avoid interference. But what I want to tell you is, I want to give you design guidelines. So minimum number of teeth for different types of gears. If you were to have 14.5 degrees composite gear system, and 14.5 corresponds to the pressure angle, the angle made by the line of force with the line perpendicular to the line of centers. So a composite angle, which is 12. If you were to go all the way up to 20 degrees full depth, you should have 18 as minimum number of teeth. If you were to go with 14 degrees, 14.5 degrees full depth, your minimum number of teeth should be 32. So these are the design guidelines. So what you should do is, whenever you are trying to design a gear, just follow these guidelines. So there are different types of gear materials. You can make gears from different types of materials. So commonly used materials are steel, cast iron, you can use nylon, and there are some exotic materials like tungsten, or maybe I have seen plastics, ABS, gears, depending upon the application, weight criteria, and the power that is transmitted by the gear. So there are different types of gears. So how do you design gear? So design. So when we design the gear, there are two important things. One is strength, which means the gear should be strong. And the second thing is wear, which means the gear should not wear very quickly. So as we talked about the strength, if you think about the basic way the gear is loaded, the gear can be visualized as a cantilever beam. So as long as this gear is strong in the bending, which means the gear profile withstands the contact forces, it does not fail, the gear should be okay. In terms of wear, since two gears are coming in contact, the localized stresses are super high. So the local stresses, they are much higher. So we want to make sure that the gear is able to withstand those very high local stresses. So what we are going to do is we have to design the gear from one criteria and check the gear from the different criteria. So we want to design the gear based on the strength criteria and check the gear based on the wear criteria. So what I'm going to do is I'm going to give you a basic design equation for the gear. Then we will talk about various correction factors that are used in gears. And then I will give you a step-by-step recipe for gear design. And then at the end, I want to work out one or two problems. So before I start the mathematical derivation for the gear design, I want to take a minute and ask you if there are any questions. Are there any questions? I don't see any. You are welcome to unmute yourself and ask questions or type the question in the chat window. So let me write, or let me design, or let me derive the gear using the strength criteria. So gear design using beam strength. This is also called as Lewis equation. The basic idea is this. If you look at the gear, we are going to look at one single gear tooth. This gear tooth, and if I were to extend this, you are going to have a force, and this force is going to be tangential to the gear. This is WT, that will rotate the gear. And so this is the center line. So this is the center line, this is the center O. And this gear had maybe certain pressure angle. So maybe 14.5 or 20 degrees. So if I were to draw a line that shows me the line of action of force, and this is called as WN, This angle is pressure angle, and this pressure angle is usually called phi. Since you have two forces, or you have a force that is at an angle phi, you are going to have a force which is perpendicular. This is called as the radial force, WR. So we have three forces. WT is the tangential force. WN, which is normal force, and WR, which is the radial force. And WT is responsible for transmitting torque, which means torque is equal to WT multiplied by the radius. So torque is equal to WT multiplied by the radius of gear. This is the face width, is called as B. What I'm going to do is I'm going to construct an inner circle or inner profile, something like this. For simplicity, I'm going to construct an inner circle or inner profile for simplicity. This is going to be point B. This is going to be point C. So what I'm going to do is I'm going to look at the bending moment at the root of the tooth. This is the root. And I'm going to find out the bending strength, or omega B, sigma B, which is given as M divided by I multiplied by Y. If I were to look at M is the moment. If this distance is H, moment is WT multiplied by H. If you were to look at I is nothing but B T cube by 12. If you were to look at Y, that is T by 2. So I need to tell you what is T. T is same as the previous one, which is the tooth thickness. So think about it like you have a beam. And it's a cantilever beam. And on this cantilever beam, you have a force. That force is causing beam to bend, and the dimensions are, this dimension is T, this dimension is B, and the force is at height H. And if it makes sense, what I can do is, let me show you. The beam is something like this. That probably would make sense. This is WT, and this is H. And you have the rectangular cross section with B and T, where T is the depth and B is the width. So, you have T. So I would show you the rotated cross section here. This is T and this is B. So it's BTQ by 12 as moment of inertia. So once you substitute this equation, and when you simplify, this equation can be written as WT is equal to sigma B multiplied by B T square divided by 6H. Now, this equation comes from the plane bending equation. What that means is, if I were to know the dimension of the tooth, then I should be able to find out the unknown parameter. It could be WT or it could be sigma B. One thing to observe, that T and H, this is very important, T and H, they are both dependent on module. So what I could do is I could replace this entire equation with an expression something like this. I can say T is equal to maybe X times module, or I can express this in terms of X times, say, pi times module. And I can say H is equal to some other coefficient, K times pi times module. So this entire expression can be written in terms of module. And that's what I'm going to do here. So when I simplify, my equation becomes, and this is the design equation for gear. So I want you to see this a little bit carefully. Sigma B multiplied by B multiplied by X square. Then pi times M is circular pitch. So I'm going to write circular pitch at PC divided by 6 times K times circular pitch. That gives me an equation which is sigma B multiplied by B times circular pitch multiplied by X square by 6K. And I will give you a minute to absorb what is written over here. Now I'm going to replace this X square by 6K with some other constant, and that gives me the most important equation in gear design, which is WT is equal to sigma multiplied by B multiplied by, I'm going to write PC as pi times M multiplied by a factor or constant Y. And I'm going to spend 1 minute talking this equation. WT is the tangential force. Sigma is the strength of the gear. Strength of the gear is the material property. Now, what are the units of the strength of the gear? The units are Newton per millimeter square. B is the face width. Pi is also a design. I mean, just it's a number. So there is no anything. There is no unit associated with it. So B is given in millimeters. Pi is a number. As you can see, Y is nothing but a number because X is the constant of proportionality. K is constant of proportionality, but module is given in millimeters. So as you can see, the units on the left-hand side match with units on the right-hand side. On the right-hand side, you have Newton per millimeter square multiplied by millimeter, multiplied by millimeter. So you land up with Newton, and on the left-hand side, you have Newton. So this is the most important equation in the gear design, and this is the first equation that you would choose. Now, what is Y? This Y is called as the Lewis form factor. And what is this Lewis form factor? Lewis form factor is sort of a correction factor because our gear tooth has this involute profile. Since gear tooth is not a rectangular beam, since gear tooth is not a rectangular beam, we have this Lewis's form factor that compensates for the changes in the cross section, from uniform cross section to uniformly varying cross section. And if you look at the Lewis's form factor, this Lewis's form factor is given for different gear profiles. So Y, which is Lewis's form factor, is given as 0.124 minus 0.61684 divided by T for 14.5 composite and full involute. Y is equal to 0.154 minus 0.912 divided by T for 20 degrees full depth involute. And Y is equal to 0.175 minus 0.841 for 20-degree stub. So these are the Lewis's form factor for different gear profiles. So I'm gonna stop here and give you 15 minutes break, and we will continue the discussion when we come back. If you were to look at the Lewis's form factor equation, this equation is a very simple equation. Force is equal to stress multiplied by area multiplied by some constant or some factor K. So this equation is giving a relationship between the force and the stress. So this sigma stress is sometimes called as the working stress. So Lewis's equation is a relationship between force and stress. Multiplied by a correction factor. And this correction factor is used because we are deriving this relationship based on some approximations. And these approximations are maybe we are trying to find out the stresses on the beam strength equation using the bending equation, where the cross section is assumed to be plane and uniform, but for the gear, it's not uniform. And this stress, which we denoted as sigma, is also denoted as sigma W. And this sigma W is called as the working stress. So I need to write this equation down and express this expression. Sigma multiplied by B multiplied by pi multiplied by M multiplied by Y. This equation can be written as sigma W times B times pi times M times Y. And this sigma W is called as the working stress. Now, why is it called as the working stress? The working stress is because this is not actually the allowable static stress. So let me tell you what is the difference between the working stress and allowable static stress. So working stress, sigma W, is allowable static stress, which is sigma multiplied by a factor which is called as CV, or the velocity factor. So this is static stress. Static stress means the assumption is if you have a beam, as we are assuming when we try to derive the equation for gear, we sort of assume that this is the beam. This load WT is considered to be stationary. It's not moving or it's not changing. But if you were to look at the gear is not a structure. Gear is a component in motion. It's a moving thing where the stresses are varying. So you cannot use a static stress property of the material when the material is loaded under varying or fluctuating or changing or traveling load. So this velocity factor takes this static stress and converts that into a stress that we can use when we are trying to design the components that are subjected to traveling loads. So sigma multiplied by CV gives us sigma W, which is the working stress that is going to be used in the expression. So how does CV affect the, the sigma W? CV is given by this equation 3 divided by 3 plus V for ordinary gears with velocities up to 12.5 meters per second. And this velocity is the pitch line velocity, Vp, which is also given by pi times d times n by 60. So as you can see, this CV is always going to be less than 1. It will never be equal to 1. If CV equal to 1 means V is equal to 0, which means the gear is stationary. So CV is going to be less than 1. What this means is sigma W, the value that we will use in design, will be less than sigma. And this is a very common approximation that is used for designs when the loads are moving or traveling or changing. So we reduce or we add an additional factor of safety. But that factor of safety depends upon the velocity. So CV is a factor that reduces the design strength by the factor that depends upon the velocity. Different values of CV are given in the textbook. I would just list them. CV is equal to 4.5 divided by 4.5 plus V for carefully cut gears up to Vp is less than equal to 12.5 meters per second. If you have gears that are accurately cut for accurately cut gears where Vp is less than equal to 20 meters per second. If you have gears that are precision cut, it's 0.75 divided by 0.75 plus square root V. For precision cut gears. And if you have gears that are non-metallic, for non-metallic gears, the equation for CV is this. So if you have a gear that is made up with ABS, plastic, or nylon, then you would use this equation. Now, I want to clarify something. If you think about this equation for CV, equation for CV depends upon V. And I need to write this down. So CV depends V, which is the pitch line velocity. If you look at the equation for the pitch line velocity, that depends upon pi times d times n divided by 60. Now here is the chicken and egg problem, and I want you to understand this very, very carefully. D is given as number of teeth times module. D is given as number of teeth times module. And what that means is we need to determine module for design. So this is to be determined. So this is TBD. So let me rewrite the equation, the fundamental design equation for gear. Sigma W multiplied by B multiplied by pi multiplied by M multiplied by Y. In this case, usually number of teeth is something that is known or decided. So for an example, if we want to minimize or if we want to avoid interference, we know that we need to start with 18 minimum number of teeth. So which means the value of T is known, but the value of M is not known, which means the value of diameter when we are starting the design is unknown. Since the value of the diameter is unknown, clearly the velocity is unknown. Since velocity is unknown, velocity factor is unknown. Since velocity factor is unknown, that leads to sigma W, which is CV multiplied by sigma O. This is known. Sigma CV is unknown. Sigma W is unknown. So if you look at the right-hand side of the equation, sigma W is unknown, module is unknown, Y is known, and many a times B is expressed in terms of module. So B is expressed in terms of module. So this equation has two unknowns and one equation. So it's a classic design problem wherein we have more number of unknowns than available equations. So how do we solve this problem? And a simple technique to solve this problem is start with a baseline assumption. So assume certain value of CV. So what we would do is we will assume that our gear velocity is restricted between, we are going to assume a carefully cut gear, and our gear is, the centerline velocity is less than 12.5 meters per second. That would be the assumption. So we will use this value of CV and carry out the calculations, find out the module, and then check if our assumption is correct or incorrect. So if our assumption is incorrect, then what we do is we go back and make modifications to update the design parameters. So as we talked about this earlier, design process is sort of an iterative process. Many a times, all the parameters that are needed to completely design the system is unknown. So what we do is we kind of go step by step to get to the final answer. So I will work out the problem where this process will be clear. So what are the typical values of static stress for different materials? And I'm not going to list the material properties for all the materials, but I'm going to give you values of sigma O. So static strength of materials. So if you were to have cast iron as the gear material, sigma O is 56 Newton per millimeter square. If you were to use steel, sigma O is typically anywhere between 140 to 200 Newton per millimeter square. If you were to use maybe phosphor bronze, your sigma O, so bronze, sigma O is given as 84 Newton per millimeter square. And all these values, they are given in design data book, and that is table 28.4 on page 1039. So, and if you were to approximate value of sigma O, say for example, somebody gives you some exotic material, for that you don't know the accurate value of sigma O. So sigma O can be determined as sigma yield or in terms of sigma ultimate. If you were to use sigma ultimate divided by 3 is given as sigma O. So for non-standard materials. So if there is a material for that sigma O is not known, then what you do is you find out what is the ultimate strength of that material. Ultimate strength is the point when the material fails, divide that by 3, and then use that value as sigma O. Now, earlier we talked about an important concept, which is the load on the gear is not stationary. So gear loading is not static. So an important step in gear design is determination of dynamic tooth load. So determination of dynamic tooth load. And dynamic tooth load is the combination of the static load, which is WT, plus the intermittent load, which is continuously changing because of the traveling nature of the load. So WT is the tangential load, and WI is the intermittent load. Now, intermittent load actually depends upon a lot of factors. such as the pitch line velocity, face width, gear material, how accurately the gear is cut. So this is called as WD, which is dynamic load, is WT plus WI, which is given as WT plus 21 V multiplied by B times C plus WT divided by 21 V plus square root of B C plus WT. So I'm not going to derive this equation, but this equation comes from the uh, the analysis, which is called as the Buckingham analysis. So this is also called as Buckingham equation. So this Buckingham equation is used to find the total dynamic load, and different terms in this equation are V. This is the velocity of the pitch point or the pitch line velocity. Then you have B, which is the face width. Then C is something called as the deformation factor. Now, this deformation factor is sort of as error in action, or this deformation factor is a factor that sort of tells you what is the relative deformation when the teeth are coming in contact. So this deformation factor is a numerical constant, and that deformation factor depends upon error in action. So error when you are cutting the tooth, what is the error in the cutter, then the class of cut. So what type of gear you are trying to cut, whether it's a precision gear, whether it's uh, maybe very accurate gear, or it's a regular gear. Then there is something called as the tooth form. And then it also depends upon the material. So if you were to look at the table, which is table 28.5, which is on page 1040, you will notice different deformation factors are given to you for different pair of material. So I just want to list one. If we have a material, so you have maybe a pinion. Pinion is a small gear, and gear is the large gear. So pinion is usually small and gear is large. Then you have different types of gear profiles. So I want you to look at that table if you have the book in front of you. So if you have a cast iron pinion that is meshing with cast iron gear, and if your pressure angle is 14.5, and depending upon what type of error in action you have, so which is called as E, which is error in action. This is nothing but error or tolerances on gear cutter. So if you look at the gear cutting profile, I would encourage you to look at the process in which the gear profiles are cut. So there is something called as gear cutting machine. And what you do is you have a cutter and the gear blank is indexed and the cutter is the rotates, and gradually cutter is radially fed and then the gear profile is cut. So depending upon how accurate or how crude the cut is. So if you think about the error could be 0.01, it could be 0.02 in millimeters, all the way to 0.08. For different values of tolerances or errors, you have different values of C. Now, you can notice as error in action increases, this is an important observation, as E increases, value of C increases. Now, what does that mean? As the error in the cutter increases, the value of deformation factor increases. So increase in the deformation factor. So increase in the deformation factor means the dynamic load is going to increase. So this results into increase in dynamic load. So more accurate is gear cutting. If your gear cutting is more accurate, you are going to have less dynamic load. And many a times, there is a design compromise. So if you start with a very accurate cutter, then the cost of gear cutting increases. Then increase in the cost of the gear cutting means that it's going to be, the gear is going to be expensive at the end. But what that means is the dynamic load, the overall dynamic load is going to be less. Now, other thing to think about is if you start with a cutter, the cutter will be super duper accurate initially. But as you use it again and again over a period of time, the cutter accuracy decreases. The decrease in the accuracy of the cutter means that the error action would increase. And essentially the dynamic load is going to increase. So you want to be very, very careful when you compromise these two factors. There is a slightly different approach of calculating C, where you can find out the value of C using an expression. So this is the tabular approach, which means you are given two materials. So it's possible that you have a combination of different materials. So for example, the pinion is made up with steel, gear is made up with cast iron. And then for different value of E, you have a different deformation factor. So if you look at the table, take 28.5, it will give you different combinations of material, and then it will give you different values of deformation factor. But sometimes it could happen that you are given the material that is not in the table. So what do we do? In that case, we use this equation. So unit for C, unit is given, C is Newton per millimeter. And why C is Newton per millimeter? Because if you were to look at this equation, C is multiplied by B, where B is the face width in millimeter. And that is added to WT, which is in newtons. So this guy here is in newtons. So this product has to be in newtons so that we can add dollars to dollars or pesos to pesos. That's why unit of C is in Newton per millimeter. The equation that can be used to find out C is given as K multiplied by E divided by 1 divided by EP plus 1 divided by EG, where K is a factor that depends upon the tooth form. So this is a factor depending on tooth form. So this value is 0.107 for involute with 14.5 degrees. This factor is 0.111 for 20-degree full depth, and this factor is 0.115 for 20 degrees stub. EP is the Young's modulus for pinion. For pinion. And EG is the Young's modulus for gear. And as you know, E is the air action. One thing that I want to talk about is error action is dependent on velocity of the gear. So if you are going to go this route, you need to know what is the value of E. So if you want to use this equation, we need to know what is the value of E. And to find E, we are going to use to find allowable error action, use table 28.6, where the error action E is listed as a function of pitch line velocity. So error action depends upon the pitch line velocity and the type of gears. So if you have commercially well-cut gears, Then you have something called as uh, uh, standard cutters. You use those to cut the gears. You can refer to table 28.6, and that gives you the pitch line velocity and the error action. So for example, if your pitch line velocity is 5 meters per second, your error action is 0.06. Alternate ways to find the value of E is to use table 28.7. Table 28.7, where the maximum possible or permissible error action is given in terms of module. So the E is defined in terms of module. So depending upon the type of gear, whether you have first class, commercially cut, or you have carefully cut, or you have precision gears, you have different values of E for different values of module. So I would ask you to refer to table 28.7. The next thing that we want to talk about is we found the dynamic load. So WD is the load on tooth when the power is transmitted. But the question here is, and this is the question, let me state the question. Can tooth withstand WD? So the question is, when WD is acted upon the tooth, can tooth support this load, or would it simply fail? And for that, we want to find out the permissible static tooth load. So determination of static, or the right word would be endurance, strength load. And this endurance strength load is dependent on the capacity to withstand fatigue. So this equation is given as Ws is equal to sigma E times B times pi times M times Y. And you have seen this equation before. This is the same equation as Lewis form equation from beam strength. The only difference here is sigma E is the endurance strength of material. This is endurance strength of the material. And just a quick recap, what is endurance strength? So if you were to load a specimen in a fatigue loading for infinite period of time. So if you set up an experiment and if you apply the load for say infinite period of time, typically that is taken as 10 to the power 6 cycles, the amount of stress that material can withstand when subjected to 10 to the power 6 cycles is called as the endurance strength. And I'm sure in EGR 444 or the previous classes, you probably looked at SN diagram, SN curve, wherein what happens is initially you have this type of behavior. So the material fails and then it sort of flattens out, where the material can in theory withstand the infinite cycles. So this is sigma, this is number of cycles. So endurance strength is the ability or the fatigue strength of the material, ability of the material to withstand the repetitive load. So this endurance strength of the material is the material property, and we grab that from table endurance strength, and this is also called as flexural endurance strength. And there is a difference. Why this is called as the flexural? Because this endurance strength is determined in bending. This endurance strength value is not determined in the torsional testing, torsional 3-point testing. This endurance strength is used in bending. So that's why this endurance strength is called as the endurance strength flexural or bending endurance strength. If you were to look at table 28.8, it will list the values of the material, the value of hardness, and the endurance strength of the material. And this is something important, that the fatigue strength of the material is dependent on the hardness, and this needs a little bit of discussion. So what I want you to think about is I want you to think about the gear tooth. And what I'm gonna do is I'm going to heat treat. So this material, this will be heat treated. So I'm gonna use some sort of heat treatment. And this heat treatment could be quenching, annealing, or maybe some sort of short pinning, some heat treatment and the surface treatment to make the surface not only surface strong, but to make this material strong. So depending upon the hardness, the endurance strength changes. So for an example, I want you to look at table 28.8. If you have steel, if steel has 150 BHN, BHN stands for Brinell hardness number. Hardness number. So if the material is 150 BHN, the endurance strength is 250. If you were to go all the way up to 400 BHN, which is a very hard material, then the endurance strength goes all the way up to 700. One thing that you want to notice that only steels can be hardened by heat treatment. Cast iron, typically the Brinell hardness number is constant unless you go with a cast iron alloy. So if you were to use a gray cast iron, the Brinell hardness number is 160, endurance strength is 84. Now, so depending upon the material we choose, depending upon the hardness, we decide we can control the endurance strength. And using that endurance strength, we determine static strength. Ws is equal to sigma E multiplied by B multiplied by pi multiplied by M multiplied by Y. Now, at this point, we need to make sure that Ws, static strength, is greater than equal to Wd. This is the condition to check. So we have found out what is the actual load coming on the gear. This is the actual load. This is the load gear can withstand. So you have Ws and you have Wd. So we want to make sure that the static load is more than the dynamic load so that the gear is safe. So this is, if this condition is satisfied, then and only then the gear design is safe. So again, we talked about the gear design and there are minor variations, but please don't worry. What I would do is at the end of the discussion, I will give you a step-by-step recipe for gear design. So I will give you step 1, step 2, step 3, step 4 that you should follow for the gear design. Any questions so far? So the last step, is, so far we have done the design based on the beam strength. So we have used the equation, Lewis's equation, to find out the module. Then we checked if the beam strength equation is satisfied. But the last equation is determination of the wear tooth load. So determination of wear load. Now, let me give you some practical interpretation of this. Now, if you think about the wear, why does anything wear? So if you think about the mechanism of wear, the wear mechanism is complex and it's a study in itself. But I want you to think about, in the case of gear, you have very high loads that are acting on the gear profile. So, and this load is concentrated on a very small region. So this gear load is concentrated on a very small region, which means the localized surface stresses. So localized stresses are very, very high. So even though the stresses uh, inside the material, they may not be high, but the stresses that are on the localized surface will be very, very high. And that could lead to small material removal. And that is a microscopic material removal. It is not macroscopic. So you won't see chunks of metal coming out, but extremely teeny tiny particles can come out. And these particles eventually will lead to wear of the gear. This is called as pitting. So if you were to look at a gear, you would many a times you would notice small pits on the gear. These are the macroscopic indentations that occur on the gear surface because of the high loads. Now this load WW, this is given as dP. So wear load is always determined for the pinion multiplied by B multiplied by Q multiplied by K. This is another equation determined using Buckingham theory. So in this equation, dP is the diameter of the pinion. B is the width of the pinion. Q is called as the ratio factor. And this ratio factor is given as 2 times velocity ratio divided by velocity ratio plus 1, which is nothing but 2 times the gear number of teeth on the gear, TG plus TP for external gears. So if you have gears like this, so you would use this equation for Q. If you have internal gears, the Q is 2 times VR divided by VR minus 1. VR is nothing but velocity ratio. Velocity ratio is TG divided by TP. TG is number of teeth on gear, number of teeth on pinion. So this becomes 2 times TG, TG minus TP. For in the case of internal gears, So you can think about the gears that are rolling inside. All right. So then next thing is, what is this K? K is called as the load stress factor. Or material combination factor. And this load factor is given as Newton per millimeter square. And this load factor can be determined either using an equation, and I will give you both. So K can be found out using sigma ES square sine phi divided by 1.4, 1 divided by EP plus 1 divided by EG, where sigma ES is the surface endurance limit in Newton per millimeter square. Phi is the pressure angle. EP with the Young's modulus for pinion, and EG is the Young's modulus for Q. Now, the alternate way of doing this is we can use table 28.9. So if you look at table 28.9, you have material, you have Brinell hardness number, and you have sigma ES. So for example, if the value of steel, the material is steel, the Brinell hardness number is 150, and then sigma ES is equal to 350. Now, here is something I want you to caution about. Sigma ES is different than sigma E. And I want you to take a minute here, pause, and go back to the table that I showed you earlier. So for an example, the earlier table I showed you is this. If you look at table 28.8, the material is steel, hardness for 150 BHN, and value of sigma E is 250. Now check here, table 28.9, the material is steel, BHN is 150, but sigma ES is 350. So I want to clarify the difference between these two. Where is the surface phenomenon? So where is the surface phenomenon? And endurance, or the bending, is the core phenomenon, which means when you are thinking about the load, which is W, even though the hardness BHN is 150, the surface strength the surface strength here is 350. So the endurance strength here is sigma ES, and the endurance strength which is here, which is sigma E. And this is a very important difference. So this is the strength at the case or strength at the surface. Strength at surface, and sigma E is strength at core. And these two are two different properties. For an example, strength of the core is achieved using the heat treatment. Strength of the surface can be achieved using the surface treatment. So what you can do is you can temper the surface. You can do a process like short pinning, where you take uh, uh, sort of hard balls and impinge them on the surface, or some sort of case hardening. So you can actually do something like case hardening and increase the surface endurance strength, and that would increase the value of sigma ES. So please understand, when you are trying to solve for wear, sigma ES value is going to be different. Don't use 250 value for sigma ES, because that would be incorrect and your gear design would not, the numbers would just not work out. So any questions here? So next thing which I want to talk about is, if you are not given the value of sigma ES, for some reason value of sigma ES is not given, sigma ES can be approximately found out with a regression equation 2.8 multiplied by Brinell hardness number minus 70 Newton per millimeter square. So if you are given a steel that you don't know a property of, then you can use this equation and find out the value of sigma ES. And at the end of the day, so the actual load coming on the gear surface. So let me write this down again. The actual load on gear surface is WD, but the ability or the max capacity, the max strength to withstand gear, to max withstand the surface load is WW. So just like the previous case, WD has to be less than equal to WW for safety. So we want to make sure that gear is strong enough not only to withstand the static load, but also the wear load. With that, we are ready to start the step-by-step recipe for gear design. But before I give it to you, let me talk about what could fail a gear. So causes of gear failure. So gear could fail because of bending. Gear could fail because of pitting, which is the surface failure. It could fail because of scoring, so which means it's a scrapping, one gear scrap against each other, the other gear. The gear could fail because of abrasion, and gear could fail because of corrosion. So the gear is made up with steel or some sort of material that is not corrosion resistant or it's not coated. So there is a chemical transformation that corrodes the gear and weakens it, and then the gear fails. So these are multiple ways with which gear can potentially fail. And we want to compensate, or we want to make sure that when we design the gear does not fail because of these causes. Okay, what I'm going to do is I'm going to give you all a break of 15 minutes. And once we come back, we will continue the discussion on the gear design. I will give you a recipe for gear design. And then if time permits, I will work out a gear design problem. So 15 minutes break. So far, what we have talked about is we talked about the various aspects of helical gear design. And we discussed these concepts in lot detail. And there is a reason for discussing helical gear, the spur gear in detail. Because when we are going to talk about the helical gear, the steps for the gear design are exactly same. When we are going to talk about the bevel gear design, the steps for the gear design are exactly same. When we are going to talk about the worm and worm wheel design, the gear design steps will be exactly same, except there will be modifications in the factors that we use. For an example, the Lewis's form factor Y will be different for the helical gear. Other than that, the process is going to remain the exact same. So for helical gear, what we would do is we would use the same tables from the spur gear. So the process would be to design a helical gear, convert that helical gear into an equivalent spur gear and design. And that design would work very well. So that's why we talked about the spur gear design in so much detail, so that when we start the helical gear design, I can give you the recipe for helical gear design, which is nothing but a slight variation of the spur gear design. And then we can jump on to the problems very quickly. So this is where we talk about, if I have a design spur gear design problem, how do I solve this? So design procedure. For spur gear. Now for the spur gear design, what is given to us? Typically, the power to be transmitted, speed, center distance, that information may be given. Or many a times they would just say that design the gear for certain power transmission. And then we just design the gear based on some assumptions or the empirical evidence. So step one is we want to find out the tangential load. So determination of WT. And this WT, this load is actually providing the torque. So if you look at the equation for power, P is equal to 2 pi nt divided by 60, where P is the power in watts, T is the torque in Newton meter, and N is the speed in RPM. So we can start with this equation. The other equation is V, which is the pitch line velocity, which is pi times the diameter of the gear multiplied by N divided by 60. So what we do is we find out WT is equal to P divided by V multiplied by CS. This is VP. CS is nothing but the service factor. So depending upon the duty factor or duty factor, if the gears are continuously loaded or if they are intermittently loaded, based on the loading conditions, this factor is used. And again, sometimes the gears are continuously used, sometimes the gears, they start and stop. So service factor can be found out using table 28.10. If you look at table 28.10, so whether you have the steady load, you have shock load, and whether you have intermittent operation, you have 8 to 10 hours operation, or you have continuous operation, the duty factors are given to us. So for an example, if you have steady, it is 0.8, usual 8 to 10, it is 1, and for constant operation, it is 1.25. If you have shock, then it's 1, 1.25, and 1.54. So they will tell us in the problem, it will be given what type of duty cycle the gear is supposed to have, and whether it's going to be intermittent operation or continuous operation. So with this, we can find out the value of WP. Step 2 is beam strength equation. So beam strength equation is given as WT is equal to sigma W multiplied by B multiplied by pi m times y. And this y is Lewis's form factor. And the equation for Lewis's form factor depends upon whether it's an involute profile or whether at 20 degrees or 14.5 degrees. But important thing to observe is sigma W is given as sigma O times CV. So sigma O times CV, where CV is the velocity factor, times B times pi times m times y. Now, one thing that is to be observed, and this is super important, that this equation should be used for the weaker element. So to give you an example, you have a gear and you have a pinion. So this is the gear and this is the pinion. So when we are going to design, first we need to know whether the gear is weak or pinion is weak. And how do we know that? So please understand, for both the gears, the value of the face width is going to be the same. Value of module is going to be the same. Value of CV is going to be the same. So the only thing that we change is value of y, which means y for gear and y for pinion will be different because y depends upon number of teeth. So this YG depends upon TG and YP depends upon TP. So since number of teeth on pinion and number of teeth on gear are different, YG and YP will be different. So assuming gear and pinion are made up with same material, if gear and pinion is made with same material, pinion is weaker. So if gear and pinion are made of the same material, pinion is weaker. But if gear and pinion are made with different material, what we need to do is we need to find out the product of sigma O times y for the gear, and we have to find the product of sigma O times y for the pinion. So out of these two, we need to compare whether the pinion is weak or the gear is weak. So the step here is, before we proceed further, we have to find out this product, which is, and many a times what we do is we find this product and we notice that the pinion is weaker. So if pinion is weaker, is less than sigma O times y, then we proceed with pinion design. But in some cases, because of the different material, if we notice the gear is weaker, then we have to continue with the gear design. And that is an important step at this point. So this is called as, sometimes it's called as the strength factor, but this is something that we would use. Next thing is, before we apply that equation, we have to assume the relationship between B and M. So many a times, B can be considered as 9.5 to 12.5 times M. So now if you look at the equation, WT is equal to sigma W multiplied by B multiplied by pi multiplied by M multiplied by Y. Value of Y would be known. Value of M is to be found out. Value of B will be expressed in terms of M. WT is known, sigma W is known. So the only unknown is M that can be found out. So with that, module is known. So the fundamental dimension of the gear is known. Next step is calculation of dynamic load. And the dynamic load can be calculated as WD is equal to WT plus WI. WT we found out in step 1. WI is given as 21V P times C plus WT divided by 21V plus square root of P times C plus WT. And once you find out the value of WD, what we need to do is, in the next step, calculation of static load or endurance load, and that equation can be found out using Ws is equal to sigma E multiplied by B times pi times M times Y. Now please note, B, M can be, they are already known from step 2. So these values are known from step 2. So at this point, we know the value of Ws. So it is known here. So we need to check if WD is less than equal to Ws. So this is an important check at this point. If WD is less than Ws, this check must be satisfied for gear design to be safe. If this gear design, if this check fails, then we have to update the design. Continuing on, the next step is determination of wear load. And that wear load, WW, is given as dP. Remember, this always done for pinion, multiplied by B, multiplied by Q, multiplied by K. And the last step here is WD that we calculated from step 3. This is known from step 3. Has to be less than equal to WW for safe in wear. And with that, at this point, we have module, we have B, we have D, and we can find out all the other important dimensions from, so all other dimensions can be found out for either gear or pinion. And once you find out the dimension for gear, those dimensions, all the dimensions except the diameter would be the same for the pinion. So module is going to be the same, the face width is going to be the same, the addendum is going to be the same, dedendum is going to be the same. And then you can start sketching the gear pair. You can either use SolidWorks, or there are online tools wherein you can substitute the value of module, value of face width, the pressure angle, and they will create the CAD geometry for you. As a matter of fact, I don't know if our SolidWorks has it. SolidWorks has a gear drawing module wherein what you do is you can just enter the particular module, particular type of gear and pressure angle, and it will actually sketch the gear for you. It's all parameterized. So these are the steps that we need to follow for the gear design. And with this, I'm going to stop here and I will work out the problem in the next class. If you have any questions, feel free to ask. So I'm going to stop recording, but I'm available to answer any questions you may have.